Hi folks, this is going to be the final lesson in dynamics. And in this we're going to look at satellite motion. Now satellite motion is an extension of what we were looking at with projectile motion, and if you look at the learning intention for this is number 6.8, I can explain satellite orbit in terms of projectile motion, horizontal velocity and weight. So if you think about what we were looking at with projectile motion, we had an object, so we had a ball and it was projected horizontally out. It would continue to move with a constant horizontal velocity and it would accelerate downwards due to gravity. And so this is what we're going to be doing with satellite motion. To highlight this point and just to give you a kind of a visual idea about what it is, I'll first of all tell you about it's called Newton's canon, or Newton's thought experiment, and it goes something like this. So we have our ball, and if I take the ball and I throw it across the room, the ball is going to go in a curved path. I'm sitting in my chair here. I'll throw it across my table, there's my laptop, and it'll go across like this. But if I take the ball and if I throw it even harder, well, I'm going to hit the window that's right in front of me and it'll bounce back. But if I were to move this whole setup to being outside, what would happen is I would throw it even harder and it would still move in a projectile path, but the projectile path would be longer. I throw it harder, so it's going to go further. And yeah, I can try this. I'm going to now stand up and go to a park. I'm going to take my ball and I'm going to throw it as hard as I possibly can. And then I'm going to throw it, and it's going to go an awful lot further. Now, if we imagine that I could take this to the next level and the next level and throw this incredibly hard. The harder I throw it and the faster that I launch it is gonna go further. And so this time I'm gonna launch it and it's gonna go so far that if I am standing, I'm standing on the surface of the earth, it's still going to move in the same projectile path. But before, if we've had our flat horizontal ground, which is what we walk around in, and all those mad people who claim that there's a flat earth think, well, it looks flat, but it's not actually flat. So if we were to throw this ball hard enough, it would start to follow the curvature of the earth. And indeed, if we fired the ball or threw the ball hard enough, and if it was obeying projectile motion, it's going to move with a constant horizontal velocity. So if it's moving with a constant horizontal velocity and it's always accelerating down at every point on its journey, if it's always accelerating down towards the center of the earth, it's a projectile. That's what projectiles do. And so let's take it to the very, very fullest extreme that we can. Let's just go over here. And now, so here we have the earth. It's suddenly become massive. I'm going to stand on the earth. I'm going to throw the ball. And I've thrown it just right. And then this is the point. I've thrown it with just enough horizontal velocity so that it's traveling horizontally out, but it's also falling and accelerating down towards the earth at 9.8. But as it falls down, the Earth is curving away beneath it. And so it's going to keep doing this. It's going to keep, oh, hang on, I better make sure you can still see it always. It's just going to keep moving like this. Until it comes round and hits me in the back of the head. Now, you might think, well, this is completely ridiculous. And it is ridiculous because I'm not going to take a ball like this and I'm not going to be able to throw it with enough horizontal velocity to actually make it go all the way around the Earth. A big thing is air, and that's a real problem. That as hard as I throw this, if I throw this incredibly quickly, then there's going to be a lot of air resistance. However, if I were to go up into space, so I'm now in space, there is no air. There is no air, there's no friction. So projectile motion actually is the one place that does actually work. So if I launch my ball or satellite with a great enough horizontal velocity, it's not going to slow down, it's going to keep that horizontal velocity. And if I get that horizontal velocity just right, it will actually move in a proper projectile path forever. Nothing will slow it down. There's no friction, no air. And so nothing will slow this down and you will have a satellite in orbit. Now what actually happens is that if you've ever seen a rocket take off, or a rocket, space shuttle, anything like that, launch from Earth, then what you'll see, and you'll be standing on the ground. So let's see, let's make sure there. So you're standing on the ground, and you see the rocket, and the rocket starts to take off. Now initially the rocket goes straight up, but as the rocket gains altitude, you'll see it start to pitch over. And so as you're looking at pictures, and you can see many of these on YouTube or wherever, you can look at the Falcon Heavy or indeed archive footage for the space shuttle launch, that you'll see it launch straight up, but then you'll see the pictures that as it launches up, then it starts to bank over. And what it's actually trying to do there is not only has it got to gain enough altitude to get out of the atmosphere, but it's also trying to gain horizontal velocity, because that's the key. We've got to have just the right horizontal velocity so that it does move in this stable orbital path. And so as the rocket takes off, it goes up, but then it pitches over, and it keeps pitching over to gain the horizontal velocity required so that once it gets up into orbit, it can stay in that orbital path. When it's moving, in its orbital path, it's going to have constant horizontal velocity, and it's also going to be accelerating downwards. Now it might not be at 9.8 at this point. By the time it gets up into space, the gravitational field strength at this altitude will not be 9.8. It will be less, but it's not less that it's not nothing. One of the common misconceptions, and I'll talk about this a little bit later, one of the common misconceptions is you go into space and you're weightless. If you're weightless, it means that there is no gravitational field strength acting on you, which is not the case. And so there will still be gravity, It won't be 9.8, but it won't be much less. If you go to the altitude, I think on the International Space Station, gravitational field strength is about 8. And so that's still a significant amount. So it will have a constant force due to gravity pulling it down. And so we'll have Fg, which is the same as weight. It's mass times its gravitational field strength at that point, at that altitude. And indeed, as it's around here, the satellite will still have a constant horizontal velocity in a vector sense. Before it was pointing over here, now it's pointing over here. But the magnitude of the velocity is going to be the same. So constant VH. I'm going to cheat and just write VH. So constant VH, and still gravity and the force of gravity is going to be pulling it in towards the center. And indeed, it would be exactly the same over here. Hang on, oops. Constant VH, Fg. Okay, and that's satellite motion, and all satellites are spinning around the Earth in this way. Once we've used the fuel to get them up to this point, then we can switch off the engines and they'll just move around the Earth under their own inertia. We don't have to provide any extra thrust to keep them that way. If we want to bring them back down, or if we want to change the altitude of the satellite, then we would either slow it down. If we slow it down, it's going to drop in altitude. If we slow it down too much, it will eventually come back to the Earth. But if we speed it up as well, we can get a greater orbital altitude. We do more of this in space physics, and we'll talk a little bit more about satellite motion in space physics again. Okay, in the next bit, I'm going to talk about weightlessness. So, weightlessness. You go up into space and you float around, so you must be weightless. But does that make sense? If you are in a gravitational field, gravity is acting on you, and therefore you will have weight, because weight is your mass. Your mass never changes times gravitational field strength. So you see pictures of astronauts floating around on the International Space Station, and you're thinking, well, they're weightless. But it's not the case. And so let me try and explain what's going on there. Now, if you're standing and you look down at your feet, you see that your feet are on the ground. If you were to get on a chair and then jump off of the chair, you would know that you hit the ground because you would feel the pressure on your feet. And you feel the pressure on your feet is because gravity is trying to accelerate you downwards, but the floor, or whatever it is you're standing on, is stopping you from accelerating downwards. So, there you are. You're standing there on the ground, and your weight is pushing down on the ground. And so you're going to have, we look at a great foot. So that's you standing on the ground, and your weight is pushing down here. So your weight is pushing down, and Newton's third law says that there must be an equal and opposite reaction force pushing you back up. And so the reaction force from the ground pushes up your foot. I'm going to call it R for reaction force. And that pushes down, and that's what creates the pressure. That's how you know that you're standing on something. because it's pushing you back up and you're feeling that pressure. Now, if you suddenly took away that, you would start to accelerate downwards and the pressure would be gone. Okay? You wouldn't feel any pressure on your foot anymore and you would be accelerating downwards at 9.8. Now usually this is bad and a number of things happen if we're on Earth, namely that as we start falling, well, I don't know, we've tipped upside down now and we're kind of going, ah! And so we're falling through the air, and we know that we're falling through the air because the air is rushing up past us. And as we fall faster and faster and faster, our cheeks are going, and so we have a definite sense that we're accelerating downwards. And when we first start to accelerate, then it's that old thing of being in a swing where you go down and go, and so you know that you are accelerating downwards, but imagine that you are in like a lift or something like that, and you're standing in the lift and suddenly the cable snaps. Now you're going to initially know that you're going to start to accelerate downwards because you're going to feel that kind of swing roller coaster. Your guts are going to come up and you go, whoa. But once you get over that, once that initial movement has happened and you're accelerating downwards constantly, you're not going to necessarily feel that. And if the lift was falling in, say, a perfectly controlled manner and there was no windows in the lift, then you're not actually going to know that you're falling down at all, other than the fact that if you're falling down at the same rate as the lift, you're not going to have this pressure on your feet. This is being accelerated downwards at 9.8, and this is going to be accelerated downwards at 9.8. Now, I don't know how well this will come out in a video, but certainly what I would usually try and do is, so if I take this and then if I drop it, you won't be able to see it at all, but you can try it at home. And what you're trying to do is you're trying to accelerate your hand downwards at the same rate that the ball is accelerating down. So the ball is going to fall at 9.8 meters per second squared. It's going to accelerate downwards. And if you can move your hand downwards at the same, if I was smart, I could film it in slow motion and show you. But as your hand is falling at the same rate as the ball, and if it's hovering just above, then you don't feel that the ball is in contact with your hand, because it's not really in contact with your hand. So it's coming down at the same rate as you. Now take it to the next step. Imagine that you turned out all the lights and you were doing this in a green screen and you had a green suit on, so that all you had was your hand and the ball. And so here you've got the ball, and as your hand is accelerating downwards, then it's moving like that. But because you've got the green screen and you just turn everything to black and just everything goes, then all you're actually going to see is a hand with a ball hovering weightless above it. Hopefully that makes sense. It's kind of hard to do through a video, but essentially what I'm talking about is that you're panning the camera down, your hand's moving down, you've switched everything off, all the lights are off, and all you can see is light and ball, and the camera is moving down at the same rate, and you're just seeing this ball hover above your hand. But because the camera's moving relative to the camera and relative to the ball, it looks as if you have the ball hand and it's just hovering there and it's just floating. And that's essentially what you're seeing. What you're seeing when you're seeing the astronauts float around on the space station, you are just seeing that they are accelerating downwards at the same rate as the space station that they're in is accelerating downwards. So they're not actually weightless, it's just that they have apparent weightlessness. And that's the crucial term, that's the key term. They're not weightless, they have apparent weightlessness. And they appear to have this weightlessness because they're accelerating downwards at the same rate as the object that they're in, i.e. the space station. Okay, there'll be notes on that in the course notes for you to have a look at. Okay, so that's about it. That's all of dynamics that we have so far, and I will be in touch with some work for you to do. Okay, thanks for watching. Bye bye.